Hey Jose, I was wondering if you could tell me what stainless steel is.
Yeah, sure, Ted. So, stainless steel is a corrosion-resistant alloy, primarily composed of iron and containing a minimum of 10% chromium, which forms a protective layer on the surface, preventing rust and staining.
Hey Teddy, why does stainless steel take less amperage to weld compared to steel and aluminum?
Great question, Jose. Well, first of all aluminum is a very good thermal conductor, meaning it quickly dissipates heat away from the weld area. This requires high heat inputs and thus higher amperage to achieve proper fusion and penetration. Now, on the other hand, we have steel. Steel has a moderate thermal conductivity, requiring a moderate amount of heat input during welding. And in stainless steel has a lower thermal conductivity than steel and aluminum, meaning it doesn't conduct heat as efficiently. This allows heat to remain concentrated in the weld area for a longer period of time, which can be achieved with lower amperages.
Austenitic steel contains at least 16 chromium and 6% nickel. It is non-magnetic and it's known for excellent corrosion resistance, good weldability, and high ductility. Some of its applications are sinks, railings, tanks, and exhaust systems.
Here's an example of austenitic steel. As you can see right here, this whole railing over here is non-magnetic, as you can see. Its grade is 304 and 316, and this is a real-life example of it.
Ferric steels are primarily composed of chromium from 10.5% to 18% with no or very little nickel, and they're also magnetic. They also have high resistance to stress corrosion and cracking, good thermal conductivity, and moderate corrosion resistance. Some of its applications are domestic hardware, sinks, cutlery, and tabletops.
Martensitic steels contain chromium 10.5% to 18% and a higher carbon content than ferritic steels. It's magnetic and it's known for its high hardness strength and good corrosion resistance. Some of its applications are cutting tools, cutlery, and springs.
A real-life example of martensitic steel is these tweezers right here. As you can see, if you can tell that it's martensitic, is that it's magnetic, and its grades are 410 and 420.
The base metal 304L and its filler is ER308L and ER347. The base metal is 310S, its filler metal is ER310. The third base metal is 309S and its filler is ER09L. Teddy, what is a carbon precipitation and what causes it?
Good question, Jose. The carbon precipitation is the process where carbon atoms combine with certain metal atoms, like chromium, in a material, forming hard, brittle carbide compounds that precipitate out of the solid solution, often at grain boundaries. Occurs when chromium and carbon atoms combine and precipitate out of the steel's solid solution at grain boundaries during exposure to a specific temperature range, typically between 800 degrees and 1600 degrees Fahrenheit, causing a loss of corrosion resistance.
Hey Teddy, what are visual cues are evident of carbon precipitation?
So glad you asked, Jose. So basically what we got here is, so on the back right here, you can see that's some sugaring right there. On the back side, we have a little bit of burn through, well, a lot of burn through. It's a little bit distorted. I don't know if you can see down it, but it's a little bit distorted. And it's also, you can see the little bit of a discoloration. It's like all black and nasty and everything. We don't want to see that. We want to see those nice, pretty colors. Jesus, I can't speak.
Hey Teddy, how does carbon precipitation affect the weld in the surrounding area?
Great question, Jose. Well, it can lead to a chromium depleted zone at grain boundaries, causing sensitization and making the material susceptible to intergranular corrosion.
Taking steps that reduce the time heated affected zone are things that will help prevent carbon precipitation. One of these examples is increasing your travel speed, which helps reduce the time the metal spends in the sanitation zone. Another way you can prevent carbon precipitation is using a chill block. Basically what the chill block does is it holds the workpiece in place while absorbing excessive heat when welding. It prevents weld defects like heat distortion, overheating, and burn through.
Oxidation occurs naturally on the surface of stainless steel fabrication, where the steel surface chromium level is been reduced. Pictures of nitric and hydrofluoric acids are usually used for picking stainless steel surfaces. Pickling is the process used to remove weld heat tinted layers from the surface of stainless steel fabrications, where the steel surface chromium level has been reduced. Mixtures of nitric and hydrofluoric acids are usually used for pickling stainless steels. Pickling is the removal of a thin layer of metal from the surface of the stainless steel. Here we have an example of why we would pickle steel over mill scale. So right here we have a mill scale, if you want to zoom in on that. It's pretty dirty, nasty on the top. You can see all that gunk. I'll bring this over. This is a pickled steel. It's still not as clean because we didn't do any surface prep. But as you can see, it's a lot cleaner just off no surface prep at all. Technique used in the weld passivation and pickling is nitric acid, citric acid, restricting oxygen, resulting in the natural passivation process taking longer to complete than the open exposed surfaces is sometimes necessary for more elaboratory shaped machine parts. Pickling, tank immersion pickling, spray pickling, and also circulation pickling. Both of them are chemical treatments applied to the surface of stainless steel to remove contaminants and assist the formation of a continuous chrome oxidized passive film.